Hello, and welcome to this CogniTwin demonstration. My name is Kasper Linnestad, and I work as a Senior Control Engineer in Cybernetica. I will present our work on a hybrid digital twin for the Elkem Bremanger pilot. I will start by showing an overview of the components before we get into more detail on each part. First, we have the post-Happel process itself, during which liquid ferrosilicon is refined and alloyed. The post-Happel process is observed by a set of infrared cameras, which combined with a set of machine vision algorithms provides additional measurements for the hybrid digital twin. The results from the hybrid digital twin will be presented to the operators via a graphical operator support system. Let's have a look at the post-Happel process. The post-Happel process starts by tapping liquid ferrosilicon from the electric arc furnace into a ladle. This ladle is then transported to the refining station where refining and alloying takes place, and it is of utmost importance that the liquid metal has a correct temperature and composition at the end of refining. After refining and alloying, the metal is poured onto a belt of moving molds in which the solidification takes place. An infrared camera has been installed at each of the steps in the post-Happel process. Images from the different cameras are gathered via their respective software development kits, and a set of machine vision algorithms is currently being developed. Infrared images will be shown to the operators, while extracted measurements will be published to OPC. Tapping. The goal is to obtain the temperature of the metal, in addition to estimating the amount of slag that is being tapped. Refining and alloying, we want to measure the surface temperature in addition to the fraction of the surface that is covered with slag. A hybrid digital twin consists of two parts that communicate with each other via OPC. We have a data-driven slag model, which aims to calculate the amount of slag that enters the ladle during tapping, and a system based on a first principles model. This system consists of a first principle model, a recursive estimator, for instance a Kalman filter, and a model predictive controller. First principle model is developed for mass and energy balances. The ladle is built up of different layered materials, and an energy balance is formulated for each of them. In addition, we have mass balances for 19 metal species, and we have a slag phase, which is liquid consisting of metal oxide, and it floats on top of the metal, thereby affecting the heat loss of the metal phase due to different emissivities and conductivities. For the energy balances, we are including heat loss by conduction, convection, and radiation. Refining is a two-step process. The first step is forming the slag by adding an oxygen source, which will react with the silicon and form silicon oxide. This silicon oxide then reacts with aluminium and calcium to form their respective oxides, thereby removing aluminium and calcium from the metal phase and transferring them to the slag phase. In order to get the model to represent the plant in the best possible way, we have carried out a parameter estimation campaign to fit the model to the plant data. Main parameters we have estimated are the reaction rate coefficient and the heat transfer coefficients. The measurements we have used are the temperature and composition probes that are taken at the end of each batch. We have used 1 month of online data containing around 850 batches. The parameters were estimated by minimizing the sum of squares of the measurement error. Here we can see a histogram of the error distribution for the aluminium concentration before model fitting. The mean error is not 0 and the distribution is relatively wide. After model fitting, you obtain a narrower error distribution with a mean close to 0. With a temperature profile for a single batch, we can see that the temperature rises early due to exothermic slag forming reactions and falling rapidly due to addition of alloying elements and cooling material, before finally falling slowly due to heat loss. Presently, only the initial and end temperature is available, but hopefully we will be able to get more measurements during the refining from the infrared cameras and the machine vision algorithms. The aluminum and calcium concentrations are slowly declining due to reactions with silicon oxide and thereby removed from the metal during the batch. Some of the parameters are varying with time, such as the heat transfer coefficients are changing due to lining wear. To account for these changes, we will use a recursive estimation algorithm, such as a Kalman filter. Here we see a diagram of the plant with manipulated variables and disturbances as inputs and measurements as outputs. By sending the same signals to the model and calculating the same measurements, we get a digital twin in parallel with the plant. The recursive estimator looks at the difference between the actual measurement and the model measurement to correct the model states and parameters to ensure a better match between the digital twin and the plant. This process can be summarized in 3 steps. First is to predict measurements with the model. Second is to take the actual measurements at the plant. The third is to correct the model based on the error between the model and the plant. The last part of the first principle system is a model predictive controller. With the digital twin and the estimator in place, we can combine predictions from the model with an optimization routine to calculate future changes to the plant. In this pilot case, we are creating an operator support system. So instead of having the controller make adjustments directly to the process, we will give optimal recommendations for the operators. Principal system will be extended with a data-driven slag model. So let's have a look at that in more detail. The goal for the slag model is to estimate the amount of slag tapped from the furnace. The reason for this is that the amount of slag is uncertain, affects key parts of the refining process, such as chemical equilibriums and heat loss, and it is impractical to measure directly and difficult to model using first principles. The proposed solution is therefore to apply a data-driven approach based on domain knowledge. Several kinds of data-driven models have been tested, such as recurrent neural networks, decision trees, and KNN regressions, among others. Recurrent neural networks have proved to be superior to the other models. Once a first version of the model has been developed, improving the model is an iterative process in which the first step is an in-depth model analysis. This in turn leads to an increased model knowledge, which again allows us to gain an increased understanding of the process. This knowledge can then be used to formulate improved models, and then this process can be repeated. In our first approach, only data from the furnace was utilized. And this plot shows the results for 4 different approaches. The importance of each variable was determined, which gave us insight into which furnace variables affect the slag amount the most. The next step is to extend the data-driven model with measurements from tapping and refining, including results from the machine vision algorithms. The final part of our demonstrator is the operator support system. The operator support system is a graphical user interface which displays key process variables and the recommendations from the hybrid digital twin. In this prototype, we have included 2 plots, temperature on the top and calcium concentration on the bottom. The vertical black line indicates the now time. We have historical data to the left and future predictions to the right. The light blue crosses indicate the initial measurements taken before the refining started. During refining, we will show the predicted trajectories for the batch, which show what will happen if the operator follows the default operation for the particular grading process. We'll also show the target region for each variable so that the operator can assess whether or not the batch will be produced in spec. The current status of the batch with key process variables is shown in a table. Together with the ballistic predictions, we will also show optimized predictions, which show the operators the trajectories if they were to follow the recommendations from the hybrid digital twin. The optimized recommendations are summarized in a table, which show the operators which actions to take. Hopefully, this system will assist the operators in running the process more optimally, that is, achieving the specification of the given grade and utilizing as much excess fines as possible. Thank you.